Good morning to everyone. Welcome back to the third day of GAN course. We are now ready to begin lecture 6, which will be delivered by our esteemed international faculty member, Professor Sukumar Kamalasadan. Sir, we are truly honored to have you with us. We look forward to learning from your vast knowledge and experience. Please, sir.
It's start, right? Start. Start. Okay, so we'll start slowly. I think many are coming, I guess, because of the weather. So what we will do is we will try to start looking into, like I was mentioning yesterday, uh, parts related to stability, reliability, how you can manage IBR to improve stability and reliability of the electric grid. So far we have learned how to model an electric grid and how to do power flow models of electric grid, which we did learn on transmission system, distribution system, and then we said, okay, this power flow model you can run. So power flow model you can run in the form of snapshot. So you can run the power flow every 15 minutes, every 30 minutes in operation, right? Normally power flow is used for, we say it's used for planning purposes, meaning you can use a power flow to design an electric grid. Where do you need to improve the voltage, right? What do you get from power flow? You get what? Voltages, yes. You get the voltages and angle of the voltages from power flow. So you know what voltages are. You can actually see what are the losses in the system. You can see how the power goes from the generator to the load. And the distribution system, you are more interested in losses and more interested in voltage. In the transmission system, you are more interested in how to generate generator scheduling, how many generators are connected and how do you schedule the generator to supply power, those kinds of things, right? So we know how to run a model of electric grid through power flow. That model of electric grid through power flow you can run to design electric grid, right? Same electric grid power flow model you can run when the electric grid is in operation, meaning every 30 minutes you can run this power flow, right? So if you, good morning. So if you run the power flow every 30 minutes, what happens? If you run the power flow every 30 minutes, what happens? You will be able to see the voltages of electric grid when the load changes, right? Because every 30 minutes or every 10 minutes, 15 minutes, the load keeps changing. So the load keeps changing, you can run the power flow again, run the power flow again, you can run the power flow again, right? Such power flow running every 30 minutes is useful for electric utility. Why? Because you can now know what are the changes in voltages in different points when the load varies. The load variation is very slow varying load, right? In the morning you'll have a peak, maybe sometimes, and in the evening you'll have another peak. Depending upon the duration of the weather, you'll see the changes, right? Such power flow study used by utility, we call it snapshot power flow study. Remember yesterday we talked about snapshot. Snapshot meaning one time you do the power, next time you do the power flow, you can do that power flow and then run as a snapshot study, right? Now we started working with time. Okay, yesterday afternoon, so okay, snapshot I can do every 30 minutes. When you say, oh, in between 30 minutes, what happens? Is there something changing? If that changes happens, can I include that in the power flow? if you include those changes in the power flow, it's good for me. I can really exactly know what happens on the system. So then we said, well, you can now move from steady state into little bit quasi steady state or time dependent power flow or time series power flow. So our first step was to see what are the slow moving devices. So how you capture a model on slow moving devices and understand the grid. So yesterday we started looking at one slow moving device which changes the voltage, which is a controller in the electric grid called tertiary control, which is changing the voltage by changing the tap of the transformer. So we said, oh, transformer is going to change the voltage. Can we include that changes in the transformer voltage in power flow and then rerun the power flow, right? For that, you need to model the controller of the transformer. And if you model the controller of the transformer, I can see the voltage changes that happens in the transformer. And if you see that voltage changes that happens in the transformer, I can include that voltage change and then rerun the power flow. Okay. Such power flow models are known as quasi steady state power flow. Okay. Quasi steady state power flow, quasi steady time series power flow, okay. QSTS. So quasi steady time series power flow is useful if you want to include changes, slow moving changes. So then we discussed, oh, okay, so we have a voltage regulator motor controller we can include. Can I include any other controller, which is slow moving? Yes, any slow moving controllers can be added into the quasi steady state time series power flow. For example, battery. So for example, battery pushing the power and battery pushing the power based on set points, slow. You can include that. So having said that, we looked at the quasi steady state time series power flow. For running the quasi steady state time series power flow, we looked at a power flow model which is different from forward backward sweep. Okay. So what we did was we looked at a model based on current injection or current sensitivity based model. So what we did was we tried to introduce you yesterday. It was a little late in the game yesterday and everybody was tired. So I am going to reintroduce you that for first 5 minutes or 10 minutes, which is the power flow model that you can run the electric grid. There are 2-3 advantages for this type of model. One advantage is that this is sensitivity based, which means if there is a change in the voltage with respect to the change in the power, change in the voltage with respect to the change in the reactive power, those sensitivity or those changes you can capture. That sensitivity in a transmission network we normally capture. And that sensitivity based power flow and transmission network, whatever we capture called the change in the voltage with respect to the power, we call that as a Jacobian. So Jacobian is the first course in power grid, power system. When we did in undergrad courses, we will learn what we call that as sensitivity. So group of sensitivity of several parameters brought in the form of a matrix is called Jacobian. Okay. So changes with respect to one variable and changes with respect to the other variable. That is not changes with respect to one variable with time. So it is not a derivative with respect to time, but it is a derivative or partial derivative with respect to variable, and that's why we call it sensitivity. So difference between a sensitivity and a difference between a time dependent variable or time derivative is that in sensitivity we are looking at what is the changes with variable with respect to state or variable with respect to variable. Yeah? So having said that, this approach you can bring that. In the forward backward sweep, we don't do the sensitivity for the entire power grid. We do the sensitive or change only the voltage drop in every system. So calculate the load, then you calculate the, remember, we calculate the voltage drop, then you calculate the voltage. That's how we do it. So first what I will do is I will show you this powerful algorithm comparing with forward backward sweep. We just did it one small, I think 5 minutes or something yesterday. So I'm just going to repeat that and then show you. So this algorithm, like we discussed yesterday, can also include every aspect of power distribution system, including untransposed lines, multi-phase laterals, all these names you know. Okay, everybody know untransported lines? What does that mean? It means the lines are not, transposed or switched. So what happens because of that? There will be unbalances between line to line unbalance. Okay. Multi-phase lateral, you know what that means? Remember, there's like a tree, tree comes and then you have laterals. Step voltage regulator, same as distribution voltage regulator, that's included. Zip load with star and delta connections. You have Y and delta connections for the load. Different transform types, shunt capacitors, and we have the IBRs sitting here, which are two different type of modeling of IBR we have done so far in the power flow. What is the first model we call it? IBR acting as a PQ type. What do you mean by IBR acting as a PQ type? Every IBR, when we talk about, our interest is only on the inverter. Remember? So IBR acting of PQ type means what? This inverter is not delivering any reactive power. It is actually keeping the reactive power or a power factor constant at whatever number. It could be 0 or it could be 0.5 or something. So it is going to be just staying there, pushing the power from sunlight or whatever to the electric grid. Such a model of a DER is called PQ type. Okay, it's also called negative load model, which means the P that is coming into from the DER, if the load power is positive, you see the power from the inverter is negative, or the power from the PV farm is negative. So this model will be used also to represent what we call it as a net load. What do you mean by net load? Generation minus load. Remember, net load. So if the net load is a negative, we call that as generation. And if the net load is positive, we call that as a load. So that is a representation, which is a very basic representation of the inverter with connected to energy source. So you can consider that as like a voltage source or a current source, and you can develop that as a model. What's the next type? Next type, you will use the inverter as a PV type. Oh, so now the inverter, which is basically IBRs, are now much like a what? Huh? What is PV? PV type means generator, much like a generator. Synchronous generators are represented as PV. Remember PV bus, So this IBR will now become a PV type. So how do you make an IBR a PV type? Well, you make a constant power coming off from the IBR, right, and control that power with the help of the PV farms or with the help of MPPT or with the help of battery connected to it. You control the power. What is the voltage? How do you control the voltage on the IBR? You control the voltage on the inverter side. So you actually, remember we said that reactive power is equal to square root of S square minus P square. You have a capacity you can define. Within the capacity, inverter can push or absorb the reactive power to maintain the voltage. So these are the two models. Remember these two models? We have developed these two models and studied these. So now, if you want to run this type of power flow, you have to develop the Jacobians. Okay, Jacobians. Remember what is a Jacobian? We just mentioned about the Jacobian. This is a change of the variable output reactive power with that. So the Jacobian for a radial system, for electric distribution system, is pretty simple. So if you look at a one phase, remember it has three phase, right? So there will be three inductance, 3 by 3 matrix, all the story we talked about. So, but I am talking about only one phase. So just to give an idea what that. So then impedance on one phase will be 2 by 2, right? So impedance on two phase will be 4 by 4. So you 4 elements. So that's how you have that 9 elements which comes for all the three phases. So this, when you look at it, if you divide them, the Jacobian, you'll get Jacobian like this. Okay. It's a pretty simple way. What is a Jacobian? You have to take a derivative with respect to the variable, partial derivative with respect to the variable to R. So it's a little tough if you do a long equation and then non-linear equation, you got to find the derivative. Here you can actually just put that box in here to find the Jacobian. Good. So that's the current injection. Now what is our algorithm? How do you do the power flow using this algorithm? This power flow using this algorithm is not that bad. It sounds a little bad, but it's not that difficult. I'll tell you what it does. It actually looks at the current mismatch on every point. Okay, current mismatch on every point can be represented as power divided by voltage and power divided voltage plus V square over Z. So let us look at this word here. This power divided by voltage is exactly what you did in forward backward shift. Remember that we said voltage divided, S load divided by V 2400 angle 0. So it's exactly what is being done. And what is this? Vi divided by Z, V divided by Z is basically the current, drop. So if you add the power, the current in here, so you can get the deviation of the current with the help of this equation going here, and calculated value for every bus, you can get the deviation of the current. So instead of calculating the voltage drop, which we did in forward backward sweep, what we are doing is we are calculating the mismatch in the current, and the goal is to reduce that mismatch and make it zero. Okay. How do you reduce that mismatch? Well, if you know the mismatch in the current, you can use this Jacobian and find the mismatch in the voltage. Now, once you know the mismatch in the voltage, you can update the voltage of the bus. Is this what we were doing in forward backward? Yes, this is exactly what we were doing in forward backward shift. What were we doing? We were finding the voltage, and we said that 2400 is no longer 2400, it's 2350 or something. And then we said, oh, okay, now that's what I'll update my voltage to 2350 and doing. Same procedure, except that done in a little different way. So we were talking about it yesterday. The approach difference in that approach is basically the modeling, capability, how to utilize that approach. So if you do that, you can update the voltage and you can repeat the process. So now I'm going to go with the flow chart. The flow diagram, it says that you compute the load, compute the active and reactive power, find the mismatch, update the mismatch with respect to the voltage, and then redo it. Okay. So I will be giving you a small example. I'm not asking you to do it by hand calculation. I'll give you a small example in MATLAB, so you can actually use that, and that will be like a homework assignment for next 2 days. So you can run this and then get acquainted with that. So this is basically some test. Oh, then we said something interesting yesterday. If you are going to model this on a power grid, what type of power grid models you will need, and how do you verify these models are good or not? Okay? So there is a standard library developed by IEEE for the power grid models. These models are called test library from IEEE. For a IEEE, any IEEE transmission and distribution network, this test library is available. Okay? This test library power grid models are real life power grid models, not that is artificially created. But the real life power grid model is, we call it massaged, meaning these power grid models are not exact number because that will be real life. So it's some confidentiality and things like that. So you can aggregate and reduce it with the same property of the electric grid. You give different bus names and then, hide some of the variables, and then you models are ready. Okay. So these models can be used, and you can get this model from a web. If you Google IEEE test library, you have a test library, you can get these models. So these models are coming in this category: 4, 13, 34, 123, 8500. What are these 13, 4, those things? What are they? Nodes. So in distribution system, we will always call nodes, which is basically, you already talked about the story of bus and nodes. So we covered from all the way up to so you should be knowing now. People nicely calls buses too, but it is actually 13 for 34, 123 instead of bus, you generally call as node. Okay. So nodes associated with the system. So why do we need 8500 and go forward? Because scalability. We have to test the scale. Okay. Now the results has to be benchmarked, and these are some of the things benchmarking for that. Okay, having said, when we do this benchmarking, you will be benchmarking with respect to the voltage, and the voltages will not be like a line, it will be discontinuous. You know why it is discontinuous? Because there are laterals that each laterals are ending in the last point on the electric distribution. So there are several endpoints in the and these endpoints are not connected because they are all lateral. So your graph will be looking something like this, and you can compare that with the deviations of that with other algorithms. So this is what we call benchmarking. We also talked about scalability studies, testing. So you can do that on this graph. So you can see percentage error. You will look at what is the percentage error between each phase. Oh, by the way, when you plot the voltages on electric distribution system, you will have to plot it for every phase and see phase voltages are matching because there are unbalances. So that's a challenge on electric distribution system. Good. So I just wrapped one more round review on what we have done. So you can actually compare this with a few different methods. This is a method that you can apply in distribution system also called Newton-Raphson. And this is some method that you can do current injection and then you can run it. The good news about current injection, this current injection model can be used to run for transmission system too, which means that you can make one power flow for transmission system and the distribution system, even though it is a little difficult. These are some. So you go. Okay. So it's good so far, right? Now you can also run this model, same power grid power flow model with DERs. Okay. So this is an example test case when the DERs with voltage control capability are connected on bus number 3 of 123 bus system. What happens to the voltage? Now you see this no PV voltage and with the PV voltage. So this PV with PV voltage, this voltage is pushed up, and you can see that it's pushed up, which means that this voltage on the low points are going up, and the low voltage and the high points can go down. So this voltage reduction, conservative voltage reduction, all those things you can actually study with this model. So is this a slow moving, changes in the voltage for the PV? You can actually add that and you can run it for multiple. This is actually a snapshot for one. This is phase A. This is phase B. Now with PV, you are pushing this voltage down now. You see this voltage was up and that voltage is pushed down by the PV controller, which means it's now close to 1. 1.0, 1.05 is very high. When you go look at the voltage, it pushed down. And, with PV, you are actually bringing this voltage back in here. So you can actually look at the bit points and you can control based on the bit points. Good. So that is just the summary. Now, I wanted to mention briefly about how you can run the power flow integrator. I think we talked about it in the one time, and I just wanted to bring that back up again. So if you want to run a power flow of a transmission and a distribution system together, ideally you will see transmission systems are like this, distribution systems are connected. So what you do is you exchange the power from the distribution system to the transmission system, run the transmission system model, and after you exchange that power, you run the transmission system, get the voltage on the distribution system head end, run the distribution system model back again. Okay? So this is what we call it as decoupled power flow approach, which means you are running it in tandem. You are not doing anything together. You are not running or developing anything together. You run one, you get the result, and then you run other. Now, when you run this, will you be running in multiple iterations? Yes, you will run in multiple iterations. Come to a point that errors are minimum. You take that number and run this in multiple iterations. Come to a point. So when do you know that this whole one, when do you stop for the whole thing? To know when do you stop for the whole thing, you look at this voltage at that bus which is connected and see for this loop, when you keep running, whether that voltage before and the next time is the same or if it is very close. If that is very close, we say that, well, you are come to a good point where you can actually have them connected. So if you do like that, then this whole loop is complete. This method is called decoupled method. This method is not very accurate but this method is good enough in a compromise between accuracy as well as the trade-off, rather accuracy as well as the time, because this takes some time to run it for. Good. So now I'm going to talk about there are some problems with respect to this. So if you are actually having time delay for data exchange, data loss, simulation time step, all those things can make this approach diverging, you know. And the power flow, there is a challenge for the power flow. The power flow that you run on a transmission system is run on a single phase, which single representation on positive sequence. Okay, power flow that is run on a distribution system or three phase on a phase sequence. Okay. So you may want to say, how do I run this one together? Will you run it in one phase, or will you run it in positive sequence representation or negative sequence representation? Okay. So so that is one thing. The second part is, how do you benchmark this algorithm? If it is running together in closed loop, how do you benchmark? Well, the only way to benchmark is to have something which is completely together, the transmission distribution system together. You don't have, if you don't develop something like that, the only place you have is simulation models. Simulation models is in Simulink or in EMT solver, EMT type of simulation that you need to have, then only you can actually run. Otherwise, you cannot run. And the challenge with respect to three-phase representation of transmission system and sequence representation for the transmission system and phase representation for the distribution. So what we can do, there is another challenge. Another challenge is, in the transmission system, there will be several distribution network connect. So if you look at a transmission system load point, you will be seeing 50 megawatt plus 35 megawatt. 50 megawatt will be 5 distribution system of 10 megawatt. Will you connect all the 5 distribution system, which is the 7,000 node or 5,000 node, and connect that to the transmission system, which is 35,000 node going into one point on a transmission system, which is huge? Or will you get an aggregated distribution system, one in detail and the rest in, comparable, whatever the total point, and then add? Okay? So that's basically the complexity. So it's important to understand that the distribution system cannot just directly connect to the transmission system and run because of the computational complexity. For the transmission. So that is another challenge. You cannot, you cannot run it because it's unbalanced in nature. So to avoid all that, there are methods, and I'm going to talk about that method. So the first method is your representation of the distribution system, for a transmission system. So if you look at the representation, there are two types. One is, we call it as that actually takes care of the things which you're talking about. One, we call it multiplying factor method. Another one is non-multiplying factor. In a multiplying factor method, what you do is, first we can get a per phase multiplying factor, which will not take care of the unbalanced nature of the distribution system because it is per phase. You can actually have a three-phase multiplication factor with balanced shunt load compensation. So what we are doing is, we are actually putting the unbalanced distribution system and we are compensating that with a shunt load, which is a balanced shunt load. So all the load, look there, it's all unbalanced, but the total which is going into the transmission system, you will see that is balanced. You can do a three-phase multiplying factor with unbalanced shunt load configuration. This will be completely three-phase. So you can actually see all the unbalances coming onto the transmission system, not partially. Here it is only partial, here it is the full. So you have three different options. You can actually say, this is less unbalanced in distribution system, I don't have to worry about it. Or you can do partial unbalance, or you can do full unbalance. So, and again, they are aggregated unbalanced because it's three phases are aggregated unbalanced. So you can use the multiplying factor, and there is another way which is non-multiplying factor. In this case, what you do is every distribution system is considered like that. It's not only one and then multiply with other. One distribution system, second distribution system, third distribution, all are like that. And then you compensate whether it is balanced or unbalanced or yeah, little bit confusing, right? Right? No? So I'll explain. So this is the first one. I'll not explain all seven. It's a little difficult to explain all of them. So the first one is the per phase multiplying factor method, which is the M1. We say, if you may recall in explained 7. So this is a transmission system load, 14.9 plus 5J. This is a distribution system load. Each of these phases are unbalanced, which you can see. And the total is 3.62 in 1.45. What you do is at each of these phases, you do a multiplying factor and then make 49, 14.1 and 5. So when you do 14.9, it's exactly the same, but each of the phases are different with respect to the power. And the multiplying factor that you actually calculate is found separately for reactive and active power for each phase. And you will see the transmission system is balanced, but each of those phases, the power are unbalanced. So you can actually get a multiplying factor. For example, you see 4.96 and 1.66 adds up to 14.95, 14.9 and 5. This 4.96 is coming with a multiplying factor. Each of those multiplying factors are different. You see? So you can actually do the multiplying factor different. So every phase currents are different, but the total seen at the transmission side is the same. Are you following? Yes, partially. Understand, right? It's understood? Understood? Yes. Not fully. Do we want to repeat it one more time? Okay. So what we are doing is, oh, do you understand the transmission system load that is seen by the transmission? Do you understand the distribution system load which are unbalanced, right? You do multiplication for each phase to bring it to 14.9. So each phase are doing multiplication. Pretty simple. So 14.9, when you divide it, this is the number you get for each phase, right? So you take the multiplication factor, multiply with this 1.49. So you take this 4.96 and divide it by 1.49, you will get this multiplication. And you put that multiplication factor, they are all different by the way, you see. And then you add them. So what is a shunt load? Oh, this is fully balanced by the way, which means that the transmission system will not see any unbalances on the distribution system. Very simple method, but it will lose the challenge associated with unbalance. It will not come. That is why the shunt load is basically zero. See, there is no shunt load which is acting. Make sense? Okay. Now in the next one, we decided, well, we want to see the unbalances on the transmission network. Okay. How do you get unbalances on the transmission network? You will keep the unbalances of the the distribution system just like that. You see, after you keep the unbalance of the distribution system just like that, you will get the total value 10.89, 4.36. They are all unbalanced on each of the system. Okay. How do you get that unbalance represented on the transmission system? You put a load, that's a separate load, shunt load. You see, this shunt load, what you are putting there are actually a constant load, and that constant load keeps all the unbalances there, and that all unbalances add up to 14.9 and 5. So the whole unbalance is going, but total is 14.9 plus 5. So the transmission system will see that same load and then it can run the transmission system. But every phase unbalance is going into the transmission network. So if you run a transmission network with positive sequence, you will not see any unbalance. If you run a transmission system positive sequence, negative sequence, 0, you will see all the unbalanced system. So you have a choice whether you want to use all the unbalance and run the power flow or not. You can actually do either one of them. You have kept the provision. Now this shunt load, what you are seeing, this shunt load 1.34, 1.5, they are all balanced, right? So this system is, following. Make sense? Little bit over there. I'll take two benchmark points and then I will say if both of you are okay, then I will move forward. Otherwise, we'll learn. It's good. Okay. Now you can also do this also unbalanced. So you see right here, this shunt load, what you're seeing is all unbalanced. This is the full unbalanced case in which now every distribution network, whole unbalance is seen at the transmission network, even though the total is 14.9 plus 5. So now you have a choice what you want to do. You want to do the full. So this compensator which you are using as a shunt, you are making it balanced or unbalanced, and you can actually map it accordingly. In none of these cases, you are not putting all distribution system full. You're putting only aggregated one distribution system, and then you can actually do the whole thing again with the whole distribution system connected. So you have more options which we can. So that is one, and then you can actually repeat this with whole distribution system. So this is a 4, 5, 6, 7, which I'm not going to go in detail. You can actually do each phase. You can connect it with different values and then apply, different. But you got the idea, right? So, you got individual distribution system connected and you have a compensator. You scale it up, multiply it, scale it up. In that compensator, you can add 3, 1, 2, and then adjust this. Good. So, the next part I will talk about, can you run this unified power flow? Can you run this TNT power flow without decoupling? Yes, they can put dynamic compensator. You can do a very important point. So yes, so this whole thing we are talking about snapshot. So we are talking about just one shunt compensator. You can put that and then connect it. You have the flexibility of looking at the unbalanced nature of that point with respect to time, depending upon how you define the time, and then you can change this compensator to compensate for that unbalances at that point. So that is basically going to be dynamic, with respect to. So how do you compensate for the unbalance? Well, you will be able to compensate with respect to the voltage. If you have, dynamic compensation, you can compensate with respect to the voltage at the point, and then maintain the voltage balance, right? Or you can actually add, shunt reactor. So physically, you can do the same thing what we are doing in modeling world. In fact, if you increase the dynamics and you do more, depending upon how they're unbalanced, you can also do reactive compensation using power converters. It's maybe fact devices or even the inverter sitting at that point. So, so that approach is flexible with respect to time. You can actually adapt based on it. One other part is very important is okay. Now we have it decoupled, right? Can you make this combined, meaning one power flow that runs for the transmission system and the distribution system? This is generally known as a unified approach or unified TND power flow modeling. What you do in here is to run this whole power flow model in one algorithm or one method. So if you do that, you will be representing. You need to do some. You have some challenges. Okay. The first base challenge is okay. How do you run a power flow? What is the base first thing which you need to do if you run a power flow? Huh? Yeah, but what value? What is the first thing which you need to do to run the power? I'll give you a hint. Uh, I'll give you a hint. Okay. You look at this equation. This equation needs to be solved if you want to run a power flow. Yes. Okay. Let's look at this equation. V equal to summation of y times I, right? Or the other way around. Z times I, or V equal to. So what is important? Before you find V and I, what do you need? Y. It's the first thing what you develop in a power flow, and we call in a transmission network power flow is called Y bus. So without having a network, you cannot solve anything. That network development is required. Now let us look at it. If you are coupling two power, meaning you are making unified distribution system and transmission system, what do you have to do? You have to make one single impedance matrix connecting the distribution system and transmissions. Now look at what is the impedance line representation in transmission system. One simple reactance or a resistance. What's the line representation in distribution system? 3 by 3. So this big matrix which is sitting there at 3 by 3. So that is the first challenge. Okay. If you solve that challenge, most likely the algorithms may converge. Algorithm may come back. So, um, so how do you solve this unified power flow? So I'm just going to talk about few things. So in the transmission network, you have a power equations, and a distribution network, you have a power equations. So the unified voltage equations will be the unified voltages, transmission network and distribution network, unified power, transmission network and distribution network, unified current and unified reactance. Right? So then you have to put it in one matrix and you can solve. To solve it, you need a unified Y. Okay? So I'm going to spend some time on how do you do this unification. Maybe with a small example. So what you do with the unification is you are going to, let's say this is a transmission network and these are two distribution network connected into two nodes on a transmission network. Okay. So if you were to connect these two distribution network, two nodes on transmission network, you first look at which node they are connected, node 4 and node 8. Second, you look at what will be the number of nodes in each, 4 and 3. And then you are going to look at combining the which points you are connected and the nodes. So 4 and 8 with 2 and 3, these two nodes. So this will give you, it's more like a address mapping in computers where you are going to use a stack register and you're looking at where the points are, the address of that point and how many are there in the row. So you add them together and bring them in the form of a matrix, and then you will see, for example, bus vector, position vector, and tie line vector. So this tie line is a connection point where the distribution networks are connected to the transmission network. This is one approach. You can do other approaches too. So that is suppose we are considering the radial topology of the tube. So when controlling the voltage for radial system, suppose which voltage we have to control, because the radial system at one point, suppose it is connected to the plasma system. So at this node only we have our lateral node we have to. So this is how it works. Very good question. So this is how it works. All the time, the transmission system output, which is the head end we call it, or the node the distribution system is connected, that voltage is the first point that you kind of maintain. And you maintain that voltage based on the entire electric grid load, including the distribution grid load and the transmission system stability. And you maintain that voltage. Most of the time you maintain that voltage with in limit 1.05. You cannot maintain 1.1 basically. That's the max which you can do. That is the source side of the OLTC, LTC transformer, source side of the transformer. So you maintain that voltage. So when you run a power flow, your job is to run the power flow to maintain that voltage at that point. But before running combined power flow to maintain the voltage at that point, you want to make sure that for any given voltage on the source side of a distribution network between 1 and 1.1, the whole distribution voltages are that you will do with a distribution power flow or distribution. If the distribution voltages are not good on the distribution network, you will put LTC and you will put regulators. Remember that slope which we talked about, right? So you maintain that slope proper. And you wanted to make sure that this slope, when this shifts, if you may recall, then we draw two lines, parallel lines, right? So the parallel lines are actually the voltages set by the source of the substation. See, 1.05 to 1.1 to 1, the voltage can vary, right? With all these time, the distribution should be working well. So you'll put the voltage regulator and transformer on the distribution line is working well. Then you take that distribution system. For this power flow, you don't really worry about voltages in any of these points. You only worry about voltage at that. And why do you want to run? Oh, now the next question, that's a counter thinking, right? Why do you want to run this power flow? I already maintained that voltage proper. I know it's 1.05. Well, if it is 1.05 and with that load, is that whole integrated system stable or not? Is something that we are testing. Especially with D, because otherwise it's mostly stable. It's nothing which is, makes sense? That is the idea here. So once we develop this, this battery is low, so maybe that's because it's. So with that, what we will do is we will just connect the Y bus and develop that Y bus and then add the tie line Y. So if you add that Y bus and add the tie line Y, you will get a Y bus like this. Okay. Now this Y bus has, you see these blocks are transmission system and distribution system Y. So let's assume this is a 3x3 transmission system. You'll have a 3x3. You see? So this 4, 5, 6, 7, you'll be having a 4, 5, 6, 7 matrix. 3 will have a 3 and the rest will be all 0. Okay. And then you will have this cross or X value is for the tie connecting points. So this X value is tie line correction. So if you write this Y bus, you will realize that this power flowing through this Y bus, this point needs to be based on that this tie line point needs to be added. Otherwise, it cannot solve. So we'll go with these added tie line points. So if you look at this tie line 2, 2 is this point, and 2 basically right here 2 to 4 is connection between these 2 points. 4 to 2 connection between that and 4 to 6. So these are the 4 points that come as a tie line. Similarly, in here 8 to 3, so you'll see 8 and 3, and 8 and 8, and 3 and 3, and 3 to 8. These are the diagonal element and diagonal element. So you will see the tie line tie line connection will be included. And once you have that, you can run the unified power flow with a positive sequence Y bus, stacked Y bus approach. Oh, by the way, well, this will be run in a positive sequence mode because the transmission system is positive sequence, and then you'll be running the positive sequence for the distribution system. At that time, it's balanced because distribution system is completely balanced. Then you'll have. Now, can you include negative sequence? Yes, you can do a negative sequence. So what will you take care of for the unbalanced? You run a negative sequence correction. And that negative sequence correction will go with these corrected tie line Y bus points as a negative sequence. So unbalance is coming in picture with the negative sequence correction. So you have positive sequence first when you do correction with the help of negative sequence, and then you keep loop in the loop. So you can per unitize integrator on common reverse voltage, compute the active and reactive power when it's between less, then it is yes, then you can get the output. If it is low, compare the equation, solve the equation for voltage iterations around the loop, and then you repeat. So for the distribution network, you will be 3-phase Y bus. You get a stacked Y bus approach, then you get a positive sequence representation like that. So you can do with this approach 3 additional things. Number one, you can include distribution system as a whole on the unified. Number two, you can run this approach in a positive sequence mode, which means no unbalance on the distribution, reduced. Number three, you can correct the unbalance of the distribution system with the negative sequence and bring it back on the transmission network without having to solve the 3 by 3 big matrix that we used to have to solve for the distribution system. So I'm just giving you one approach for the unified. I think there are only 2 or 3 people in the world is trying now. This is what we have tried in our lab. There are could be some other approaches. I'm not saying that this is the best. I'm just saying that this is the approach that we find is useful and we implemented it. Um, but I think there are a few people have started looking at it very closely. Uh, Many are doing decoupled because that's easy to represent and implement it. So two different options. You can do decoupled too, or you can do unified. Some advantage we saw in the unified one. Um, so this is how the Y bus will look like if you are looking at in the form of a positive representation. You will also get the negative representation. You'll get the zero representation, like I said. So this is positive, negative, zero sequence. You can actually represent this in the sequence form, and then you can write the sequence balance equation, like zero, negative, positive, and you can actually write the. You can actually only do the positive if you don't care about negative, and if you do the negative, you can do the negative, add to it, or you can do the zero. So if you look at it here, this is a per phase admittance matrix. You translate that into the sequence. So, oh, by the way, you understand that, right? If you want to run in a sequence representation for a distribution network, you have to convert the phase representation of the distribution network to the sequence representation. Otherwise, you cannot run. So the phase to sequence, which is not a big deal. There are converters, phase to sequence converters, but the point here is that you have to take the phase sequence part and then convert into, phase admittance matrix and then convert into sequence admittance. And if you convert that into sequence admittance matrix, you'll be able to you'll get this sequence, phase to sequence submatrices, and that submatrices you have to put that in here. So these are the sub representation of each of those. So now you don't do everything in sequence. Most likely you don't do everything in phase because transmission network running in phase is a challenge. So you always go the other way around. Okay, the bus is ready, right? Once the bus is ready, can you run the power flow with one algorithm? Yes, you can run the power flow now with one algorithm. You already see this algorithm before. What is that algorithm? That is a current injection algorithm that we run for the distribution network. Same current injection algorithm, you can run it for the transmission system. Some of the challenges that we faced while we do the unified is basically this, and there are some tricks to avoid the challenge. You see a bunch of zeros here, and this is something to do with any power flow challenge, and this is what we call it as, if you have a bunch of zero, the Jacobian is not invertible. You might have heard this thing in your courses, and we call it in the software call it not possible to get the invert matrix, and mathematicians call this as singularity of a matrix, and electrical engineers call it as these matrices are sparse matrix. All these things basically leads to the same challenge and problem because you cannot get any inversion, and you see that in here. You will see some sparsity here. See, this zeros are sparse, but the sparsity is okay to solve any inversion. The sparsity should not come on the diagonal elements. That is the biggest challenge on inversion. So if you do this correction matrix, you see this XX there on the correction matrix. If you add that correction matrix, you can actually avoid that. So that is something that we introduced to make the algorithm working. That correction matrix, you have to limit it to some number. If it's very high, that affects the drop. It's a compensation, exactly. So that is one challenge. The second problem that we faced was probably scalability. If you run it for 20,000 bus or 30,000 bus, it's going to be challenging. But the idea is to get this type of a framework, and if you get that framework, we get a Jacobian and we can solve. So again, the same story. What is the story? Once you build something, you have to benchmark it. So to benchmark it and test it, and you have to take it and you have to compare that with the um, unified approach and on, voltage at each points, and you compare with the voltage error. So this is a spot load at node 14. Basically, you just run one. Oh, so how do you compare it? You have unified now. You comparing it only done separately with the distribution and separately with the transmission with respect to that voltage. That's the only way you can compare. You cannot compare any other way because you don't have another unified to compare, right? So these are some comparisons error for the smaller system. You can actually add. So this is a case we added 4 distribution networks on a node and then tested it out. This is a real IEEE distribution network. It's called IEEE 123 bus system. You can compare that and then connect it with the transmission network, look at the phase error, the average. Oh, you also look at computational time because you don't want to have this take 1 day, 2 days to solve it. So that is something we tested a few test results. Okay, so we talked about the power flow. We extended that to integrated with respect to the power system. We also included DERs in there. So one of the topic which we have to do for the first lecture today is to see whether this type of framework can be used to assess the stability of the electric grid. Okay, because there is a word there on the title called stability. So I'm trying to make sure that I attend each of the pieces there. So what we can do on stability of the electric grid, we can do stability. Everybody know electric grid stability? What are the 3 type of electric grid stability? Huh? Voltage, frequency, and angle. So there are 2 type of stability. One is with respect to the parameter, another is with respect to the time. So parameter with respect to the variable or a parameter, you can call that as voltage has to be, So what is the power quality with respect to electric power system? Little bit different on power electronics, but what is the power quality on electric power system? We call it value quality. Okay. Power electronics, if you move that, then it's more important to look at the shape quality. So it's actually, same deal which we talked about the RMS versus waveform. So the value quality, we talk about what? The value of the voltage that you get could be good, value of the frequency that you get good. We care less about the angle, but that's very important. So angle, so angle is also important. That's parameter, and we look into time. We talk about the quality with respect to larger time, smaller time, and very small time. So very small time quality, we call it transient quality, and that is assessed by transient stability tools, transient stability analysis. Such tools are called TSA. These TSA tools are actually running differential equation, but you are also integrating algebraic equation together to form a differential algebraic equation model. We have something called long-term, short-term stability. For long-term, short-term stability, so the angle you will be seeing that in a electromechanical time frame. Magnetic stability you will see that in a very small time frame, and the voltage stability you will see that transient, small, dynamic, slow, everywhere. Voltage has got a wide range of problems on stability. It can be very fast change in the voltage. It can also be very slow change in the voltage. We call it a sag. So this is stability property. Why do you want to know angle stability if you already know the frequency stability? If you already understood the stability for the frequency. Is angle and frequency the same or related? Different. They're different. What's the difference between angle and frequency? Power angle. What's the difference between power angle and frequency? What's the derivative of power angle? Derivative pow- generation system. Yeah, power angle. I'm also talking about power angle of generation system. Power angle of generation system is angle per generation system. So that power angle of generation system, you take a derivative of that power angle. What do you get? There's somebody in between before acceleration. Huh? If you take a derivative angle, you'll get omega. Omega is called angular velocity. You take velocity, then you go to acceleration. You cannot jump to acceleration. So you take the angles, and you get velocity. Okay. Angular velocity. What's the relationship between angular velocity and frequency? What is omega? What's the relation between the angular velocity? Pretty same, proportional. So now is that angle and frequency related? I made a relation. And you said it's not what I mean. Okay. But so then why you want to do angular stability and frequency stability? There is a reason. I mean, you're right. You need to do angular stability and quantity. I'm just trying to clarify some basics. What is the why you want to do it's still the rate of change, right? It's not the same. The rate of change is not the same as an angle. So what's the difference between rate of change and the fundamental quantity? It's different with respect to time frame, right? So it reacts differently with respect to time frame. If it reacts differently with time frame, you have to understand the differences for that. That's the first. Number two is that frequency is a rate of change of angle, and the omega is that frequency not just only dependent on angle, it's also dependent on something else. So depend on something else. It is dependent on something else. Is it frequency dependent on power balance? Power function? So it's not just, of course, angle also dependent on the power, but fundamentally frequency is dependent on the power change or power, angle, right? So that's what you call swing, okay, which is dependent on the power changes, and power change is dependent upon how fast or how slow you can push the power, dependent upon the what we call it as inertia. So there is frequency sitting there, which is like we call it global. It's dependent on several different factors. Angle sitting there, we call it local, dependent upon each generator or each bus which is sitting. So you need to study local disturbance and local stability. At the same time, you need to find globally whether the system. That's why we study differently. Now, frequency stability, when you study, you don't study the frequency stability with the help of fundamental power angle curve analysis. You study the frequency stability with the help of load frequency balance or load generation balance. That's all. So the frequency stability, you can call it as a little bit of a not a very fine frame study. It is a very coarse frame study with respect to larger on the largest. I just fundamentally placed a 10-minute crash on stability. So when you are looking at the this kind of study, we can basically study um, frequency stability, angle stability, and voltage stability. But what is more important to connect distribution network and transmission networks, like sir was saying, is to understand the voltage profiles of the system. Okay, so this voltage profiles of the system, not just on the head end of the substation. You should be able to look at the voltage profiles on the system on key different points. The substation point, you can also look at the voltage profile on the system at the PV node on the distribution network. You can look at the voltage profile on the system on the transmission one node. You can also look at the voltage profile on the system on the another node, right? This voltage profile understanding is something that we can do directly from the power flow, which is slow moving voltage. Okay, still voltage stability is slow moving voltage, and there is a this voltage is a study is performed based on what? Why this voltage changes? This voltage changes based on the power flow, right? going from transmission network to repeater. So there is a classic study method that is already been introduced in the electric power system engineering curriculum to study the voltage with respect to the changes in the active power. And that is something called generating the relationship between the active power and the voltage for every bus, generally known as PV curves. Remember? Have you heard of this term PV curves? Yes. I think it's a stability course we teach, I guess, right? Stability course is PV curves. What does a PV curve meaning? PV. What do you mean by PV? Change in the voltage with respect to the change in the power. Where do you see the PV curve? Well, you see the PV curve on every bus. Can you do the PV curve for the entire system? Yes, you can do the PV curve for the entire system. So if you plot the PV curve for the entire system, will you see the changes in the voltage with respect to the changes in the power? Yes. So can you see that when DR power changes, what happens to the voltage at that point? Yes. So, is this PV curve um, can be studied for slow moving power with respect to slow moving voltage? Not very fast change in the voltage, not dynamic. Okay, so you have to be careful seeing that PV curve. Once you have the PV curve, what is that difference you can get? You can see what is the point at which the voltage on an electric grid collapse when the power changes. Okay. So conventionally PV curve, when you look at it, we used to draw the PV curve and then we used to study the PV curve. And when you draw the PV curve and study the PV curve, you draw the PV curve and study the PV curve, you plot the P versus V, and then you go and the PV curve looks something like this. I don't know whether you may remember the PV curve. It looks like this. I don't know why it is like carbon. I don't want to explain why it is like this because it takes some time to explain. It's basically V and V square and P are the relationship. That's what it. So when you do a PV curve study, normally we try to increase. You know how you study this? For a specific bus, I wanted to study. Every time we will put a inverter just for fun purpose. So if you want to study a PV curve on a specific bus, what will you do? This bus has a voltage is equal to 0.98 and load 10 megawatt. PV farm load minus 3. I see. You see, I put 10 minus 3. You know what that means, right? So if you have a system like this is a normal condition, right? How do you plot a PV curve? Very easy. This one, you have it. Now you change this. Okay? So conventionally, let's assume this is equal to 0 and this is not there. You change this. Okay? So let's assume that you are here. This is 10 megawatt. When you increase this, voltage start decreasing, which is a norm, and you get to a point, some here, and you will see what point you don't want to go here. You can see what point you will reach before the voltage collapse. Simple. This is a fundamental idea of a PV. So you may ask, okay, is that the only thing which you can do from the PV curve for stability? No. You can also say that, well, I am here. What will be my margin for stability? So how much P I can push on this bus before the voltage on that bus collapses? Is that useful? That's a very useful thing. If I know that for all the buses, that's something which I can understand and how much. Oh, now let us look at the DER. Is that useful when you put the DER? Yes, it is useful for us. Now when you put the DER, which is same old, that's something which I was telling. Everything when you design, you will see that relationship from the old thing, so you can understand. What happens if you put the with the BER. What happens to this arrow when you put the BER? So you just start going in this direction. So when the voltage is dropping, when you connect the PV at this point and push power, the voltage will start going in that. You see, now the fun. So now the old PV curve, which you always see only in one side, you have to now start looking the PV curve in both ways, going this way. Oh, is that logically making sense? Yeah, it makes sense. When you connect the photovoltaic on one point, the voltage is rising at that point because you're pushing the power like a generator. You have to balance that voltage. That's your job. Now you can also get an overvoltage at this point, right? Now let us look at another scenario. This PV palm output, which is coming with the sunlight like this. Now this thing is going to start wobbling. So, this is not slow moving, fast moving, but this is what's going to happen when it's fast moving. Just going up and down. Now let's assume that you load the this feeder at this point and you connect a PV right there. It's going to jump because it's going to go like here. It's not going to stay there because this is what's going to happen. It starts oscillating. And if it starts oscillating, it's very easy. It starts dropping it and collapse. So I'm not making a list here. So one list is a maximum. Second list is margin. Second thing is margin. When PV comes, the first thing what you can do is safe. When you can operate safe, at what point you can operate safe. And the thing is, and then you can also say how much control. Right? You need to control the PV from the reactive power from the inverter. Who is doing all this stuff? Our poor inverter. That's basically the one who is actually handling most of the things, So you have to size. So nobody has done this work and the research part yet. So you could actually do some study on the inverters and how you size the inverter to maintain PV stability for that specific point in wherever the inverter is connected, which is actually not done. It's a power system job. But you also wanted to make sure that how much voltage you are going to maintain with the inverter from the inverter standpoint, the box standpoint, because there is a limit there. You are actually controlling the voltage at that point. You are wanted to maintain that to 1.03, 1.04. You cannot actually maintain beyond that with the help of modulation index and everything. So you have to connect with those. That's basically some other research which we have not done, which we can do later. Is this making sense on that side? Okay. I think we can leave it like this, right? Just screenshot. So with this being said, now I am going to talk a little bit about the stability. So for this part, what we are going to focus is um, voltage. Okay, PV curve voltage. Mm, I will give you a little bit high level overview of the algorithm. The same algorithm that we just discussed, the unified algorithm, you can run this algorithm or the other algorithms in multiple forms. One algorithm that you can use it to run is multi-period power flow. Multi-period power flow is also known as time series power flow. Remember that we discussed it yesterday, time series power flow. So you can run the time series power flow for a transmission integrated system and run the power flow for each phase till the system converge. And once the system converge, you can actually change the power, and then what you can plot is the voltage stability margin. Okay? So this voltage flow, by the way, this I think you should be knowing this or remembering this. Mm. So this one, so P and P max, right? Normally, people don't represent this in this way. They represent based on the base point. So let's assume the P0 is a base point. Okay. Now the power that you're plotting, you say P, and P divided by P0, you calculate and you call that as a lambda. Okay. So which means P0 is same as the first operating point, the lambda will be 1, and then you increase the lambda. So you call this, when you study this, we call it lambda. Okay. So what we have seen in this graph is a lambda change. Lambda change meaning maximum lambda. So instead of P max, we call it lambda max. But you understood what the relation between P and lambda, which means that you are not actually, you're doing a number and you are a scalar number per unit as scalar number. So you can see here the beauty. You can study this with zip load, spot, zip. You can study spot load with constant P loads. You can study it with distribution system balance. You can study the distribution system unbalanced. All those, what will be the voltage margin? So if you look at distribution system unbalanced with constant P, you see this voltage margin is very low. So now this curve, what you see on that bus when the DER is connected is in the classical stability course when we teach, this kind of curve will only come when there is a power factor change or capacity, capacitor connected load and things like that. This is called multiple PV. I don't know whether you, and there will be a stability margin line that you plot. And then you call this as the stability margin. Some of you have taken that course, I guess. So this is how you plot conventionally. You will get a similar type of stability assessment for all unbalanced nature. Oh, this is without connecting DER. This is just the normal. You connect DER, obviously you can add that as well. Makes sense? So that is what, yes. So we also the power of yes, so the margin, yes. Each phase also can contribute to different margin. Absolutely. So you can actually put margin for each phase. And then what is the goal here? Goal is to make sure that you take the worst case scenario. So what you do is, why do we do this? If you do all the studies, end of the day you say, hey, this distribution system I know it's very unbalanced and that has got some, phases are different. And I cannot load beyond 1, meaning I cannot load beyond the current situation. Don't load beyond the 1. Because if you don't load, it will collapse. So that is something that can be used, the tool can be used to predict or say with the help of the tool. Otherwise, what happens is you don't know and you don't know the distribution network how it's connected, and you go and then connect. Actually happened in doing the interconnection for the photovoltaics. I think we will be doing interconnection study here too. So when you are connecting a PV farm to an electric grid, before the connection is done, you have to do what we call it as interconnection studies. Interconnection study is actually a study done to see what will happen if the PV farms are connected in one point, what will happen to the voltage, what will happen to the electric grid, whether you need to add any compensators, so there are some, I think in India, what I heard from IISc, there are places they are enforcing to add like StatComs, I guess, which is basically to improve the voltage on near the PV farm and some places because of some voltage related problem. So you do interconnection study. This is has to be done, and normally it will be done. I think here also probably somebody is doing that, and also the US people are doing that. But none of the interconnection study do any of these kind of study, which I think is important because you will It's dangerous, if you look at it that way and if you connect the PV farm. Because location you cannot change. So that is decided by policymakers, government, some other people. It's nothing to do with technical people. They don't do anything. It's just okay. The only thing what you can do is you can strengthen. Oh, another question. Can you make this PV curve robust? Can you make can you load four up to four? Can you do that without doing anything? Yeah, if you can improve this voltage shape, go like this, then I think you have margin. How do you improve that voltage shape better? Dynamic compensator. You should have some kind of a compensation, voltage compensation. Voltage compensations are one way to do this or take care of. But do that voltage compensation, you need to know how much, what is the size, where do you connect it, how do you compensate, how much is this. 4 is a number that you get. Well, I'm happy. I got 4, then I can find when 4 happens, what is the voltage, and then I can do all that. But there's a tool that is required for that, right? So there's one example of stability tool that you can, one example of power flow tool that you can use it for stability study or voltage stability margin assessment. So I see. Yeah. So you can actually plot this. So this is basically the PV curve upper part. It's like lower part plotting is not easy to do. So if you see plot like this, you can see this is P with the transmission system with the spot load. So if you run a transmission system without a distribution system connected, this is the margin that you see. So the T with the equivalent distribution system, that's the margin. Positive sequence T, that's the margin. Three phase T and D, that's the margin. So you see the whole thing, and you know the lambda, right? So the whole thing is going from 4 to almost 1. And in some cases, with this is a constant power load. With the zip load, even it goes all the way to 2. Oh, zip load, we are saying that is better now than the constant PQ load, which is I think is good because you are reducing the power of the load based on the voltage. So all these trend lines you can get with the help of our simple power flow. Lot of effort to put it to run that power flow, but it is not even if it's time consuming, it's not going to break anything. I mean, you just run the power flow, like 3 days after that you get it, it's okay. At least you will get these numbers. Now then you can. Uh, Now this continuation. By the way, uh, I have to say something about this. So this PV curve, generating the PV curve with the help of power flow is done by several different way. One method to generate this PV curve is known as continuation power flow. I don't know whether you have heard. I think some of you might have already heard about those things. But continuation power flow meaning you've done the power flow continuously. Okay. So you may call it as if you run the power flow continuously, you call that as a multi series time power flow, right? Continuation power flow is not that. Continuation power flow is a little trickier. You run the power flow multiple times, you can reach here. But to reach here, you will need to do some tricks. Okay, that is done by continuation power flow. So I'm not going to go with the continuation power flows. You see this power curves, PV curves plotted. This is the PV curve without DER and with the DER. What happens when the DER comes in place? If DER is pushing the power, PV curve is kind of extending because DER is getting more power onto that because it's going to the light load condition. So the PV, so you can see that. What happens to if there is a transformer taps? Transformer, you remember LTC, OLTC that is on this distribution. When the transformer tapped with the fixed tap, no tap, this is a PV curve. When it taps, you just PV curve is getting extended. So now you can say, hey, I am regulating the voltage of transformer. What will be my PV curve? I can assess that. So that is actually on the head end. So you just go with the one voltage at that point and see what is the PV curve there at that point. And you can actually do. So we proposed, and there is a paper in here. I don't know. I not put the reference there, which you can read. So that's basically the cost. Any questions?
Suppose on the same bus, we will remove the distribution system and we have to add some dynamic load kind of thing. Because in the distribution system itself, as you told, R by X ratio, that will be very challenging task to manage. So, in terms of actually market, I would like to ask here that like demand response analysis, suppose we are doing and we are managing the things, then it will be very disturbing for the transmission systems.
Yes.
So at the same time, because distribution system will always disturb the transmission system. So under this scenario, whether it will be beneficial to go for combined power flow or separate power flow, and then we can.
Very good question. The answer is kind of yes and no. Depends on what exactly you want to study as far as the markets are concerned. So let's assume that you are studying on electricity market. You are studying the active power transfer. So when you do study the active power, you will be studying at this point the power that is going, and let's say this is a transmission network. You are looking at the exchange point in here, how much power drawn at this point, how much power drawn by here affects the power output from the transmission side. So if you are going to look at that, so this is basically, I'm talking about uh, changing topic here. I'm talking a little bit about electricity market, how the electricity market runs. So in the electricity market world, how it runs is it actually look at the power that is being scheduled and power that is being consumed. Now the power that is scheduled is not the same as power consumed. You will be you will have some challenge. You will have to pay more money. Okay, so that money, whatever you pay, whether it is extra generation or whether it is extra generation adjustments, so you don't have to generate probably extra, but you have to adjust the generation. So for example, suppose you have this is a cell and this is the load, right? Here you don't need to generate extra, but you need to adjust this. You see, somehow you need to adjust this. So how do you adjust that? Well, you adjust that by putting some other device or ramping up or changing something on the generation. That is basically your cost, extra cost. But instead, let's assume that in here it goes like this and then it goes like this. At this point, you need to change the generation to another generation. So this is the market problem. Okay. So you do markets in different time scale. Everybody probably know. One is called the market ahead of time, long term planning. Second is market a day ahead. It's called day ahead markets. Then you have the market for hour, every hourly market. Then you have what is market, we call it the real time, where you are going to, at this point, how much I have to incur the cost, so I need to adjust it. So depending upon the real time changes in a day, for example, every hour or something, you may give you a signal to the load and ask the load that, hey, if you can, please stop consuming power. If it's a very bad scenario, okay? So the demand response, basically what it means is you are going to give a signal to the load and say that you either need to shut down the load or shift the load. Okay, this is done normally in what you call it's a TOU. I don't know, it's maybe same name here. Time of use tariff. Time of use is basically Every time you use the electricity, you pay money extra according to that. Not a flat rate, So there will be flat rate, but there will be extra money that is going to happen. But anyway, so the question is, in this context, how do you model the distribution network and then connect it to the transmission system? If you to model a distribution network and working as a disturbance, you can model this distribution network as a slow changing PQ load and then study. Okay. But if you are running as a dynamic case, basically for the stability, that's a different thing. That actually has to add based on the market. So market study is the operation. So that is why it is a little different. Basically, was Dr. Tiwari's okay. So what we will do, we have 30 minutes, I guess, right? We will switch gears now. If no other questions, we will move to the little bit of another topic. And that topic is, now we started looking into controlling IBRs, okay, managing controlling IBRs. So let me talk about the context. So now this is your so if you look at the electric distribution network, this is your load generation, this is your IBR, right? So now when you look at it, you will see that the I'm just making a shape here. This is with respect to time. This is the power for the load plus DER. Okay. So what we have done so far, we have looked at how much the power balance happens, what will be the voltage, how the voltage can be controlled or balanced. I mean, how the voltage can be seen with the help of power flow, right? And then how the power flow changes, right? We have not touched so far. How can you control the DERs? So to control the DER, you have to give some reference, right? That reference power to control the DER will come from the power flow and then next. Uh, yeah, controlling is difficult. Yes, it is difficult. How do you control? That's what we're going to talk about. So, so basically, if you can control, let's assume that you can control. If you can control, then obviously you can actually adjust this shape. And if you can adjust this shape, you can probably get a better match with respect to stability now. Okay. So now let us say that you have a DER at one location and you have several of these DERs. And this DER is doing this. This DER is doing this. This DER is doing this. Okay. If you add all these together, you will probably get a shape like this. Now let's assume that this DER 1, 2, 3, this is a PV farm. Okay. It is a PV farm. Most of the output from the PV farm, you will say that you cannot control because you have to put maximum power coming from the PV and then you take out. So those PV farms output P cannot be controlled in general. because you take the maximum power from it. But for those PV farms, if you have an inverter connected, you can control the Q of the inverter. Good. So that Q of the inverter you can control. So first thing which we can say, if we have any intermittent sources connected, you have some available Q that you can control from that intermittent source connected at the inverter. So you can give a set point from the optimal power flow to that inverter, and then you can track the set point. Good. That's basically Q for all the inverters, right? How do you control P? So you control P, only way you can control P is by making this DER dispatchable, right? Now this is not dispatchable. Oh, you understand the difference between dispatchable and non-dispatchable? I think we discussed this yesterday and day before. I think one of brain damage. Dispatchable generators are synchronous generators, for example. What is a property of a dispatchable generators? If you say 5 megawatt, if you ask for it, it will give you 5 megawatt. Not maybe now, within 3 seconds it gives. 3 seconds it gives through governor. Talk about the storage. This is a dispatchable. So here, if I want 5 megawatt, this guy cannot give 5 megawatt. Says there is no sunlight. So how do you make that inverter or in the PV farm dispatchable? The only way you can make it dispatchable by energy storage. That's the only way you make the PV farm dispatchable, right? Now, where do you connect this energy storage? It's up to you. Whether you can connect the energy storage along with the PV farm and then convert the DC to AC, right? Such PV farms with the storage are generally at the, we call it behind the meter, meaning not seen by the utility. It's in the rooftop or some places you always have some battery or the PV connected to the battery, and then you have some DC bus. I'm not going to draw the picture, but you can see the picture, right? PV, battery connected to DC, then to inverter, then to AC. One architecture. What's the second architecture? PV, multiple PV in one like neighborhood, one battery, again connected to DC bus, and one inverter. What's the third architecture? Multiple PV, inverter, one battery, inverter, again connected to the. What's the fourth architecture? Well, multiple PV in a long electric grid. Utility will go and say, hey, lot of PVs here, it's all changing. I'm going to put a battery connected to the inverter and to the system. I'm not looking at the individual PV control. The entire area, I'll put the battery and I'll control the battery, right? So we divide the asset, PV farms and battery, into two. One is controllable asset, another one is non-controllable asset. Non-controllable asset, for the active power, it pushes active power, whatever you want. Controllable asset, which is done in the form of, for example, energy storage. Now, this controllable asset is money. You need to find when to, how much to size, where to put it, how many to put it. If you have a tool to understand what are the problems, how much PV comes, how much you need to put, then you can design what will be the size of the battery. So normally there is a question, what's the size of the battery, where you put, how many you put. 33%, 40, 35% is the rule of thumb that you put PV farm and then you have a 33% battery with respect to the performing capacity, which is including capacity factor of the PV farm when that battery is moving. So this is how you manage the years. Is that story? You understand, right? So what we are going to do now, we are going to discuss some methods coming from the top level, meaning on the distribution network level, how you develop a tool to understand what are the changes in the PVs if you have a battery connected in different locations, what it can do, fictitious battery connect models, which you have battery connect, what it can do, and then you can analyze based on that where to connect the battery and what to connect the battery. And everything is done through battery energy. Oh, I say keep saying battery. It can be any energy storage. It doesn't really mean that it has to be battery. It has to you have to store the energy. That's the idea. Good. With that premise, and of course it's intermittent, and it may be variable. Some other variable factors can also. So that being said, I'm going to show you some methods that we have developed and implemented for controlling the DERs. Oh, when we call it controlling the DERs, you assume that controlling the batteries. DERs are, so anyway, distributed energy resources. Distributed energy resources are distributed. It doesn't really need to be PV. It is basically, yes, of course, you cannot do anything with PV. So if you want to control, what are the challenges? Challenges is the intermittent nature of DER. It causes uneven voltage profile. Penetration level can increase, the voltage profile can be optimally balanced. So the goal is to balance the voltage profile and at the same time supply how much power you need to supply from the battery to balance the power output, power schedule. So what you need is a reactive power management. You will also need active power management. Okay. So first I will talk about reactive power management and how you do that. So there are two ways you control a DER unit. One way you control is local, or we call it also decentralized. Another way you control is coordinated or centralized control. So there are two different ways you control. I'm going to talk about both of them, like two examples rather, and how you can adjust. And the good news or bad news is that you will need to have, if it is locally controlled, you don't need a communication link. And if it is globally controlled or coming from the substation, you need a communication link. And locally controlled has a challenge that you cannot get the global signal. So you will not be able to manage, for example, frequency and voltage. There are some pros and cons. So how do you do a coordinated control? So there's one approach that you can do for a coordinated control is linking optimization with control on a central location. Okay. Have you done optimization? Yes, we did optimization. And optimization architecture linking with control is generally comes under the classification of optimal control. Okay. So what do you do in optimal control? You are going to minimize an objective function and design a controller output. Okay. When you do a controller output, oh, by the way, I also need to talk a little bit on different level. So this control, if you are controlling a DER, that's generally called device level control. On the device, the DER control happens. Okay? If you control the DER or group of DER, we call it secondary level control, where you send a signal to the group of DER. If you control the DERs in entire substation and send a signal from the substation point, we call it tertiary level control, where you are going to send a signal from the substation point. If you are running an optimal power flow or a power flow, you are going to do either tertiary control or secondary control. You don't do device level control, which means that signal of the power comes to the substation, say, hey, I need this signal. That signal goes to the group of DER and say, hey, I need this from you, this from you, this from you. And then this go to each DER and say, hey, I need your contribution. So you divide them into that's how you send a signal. So when we are talking here, we are talking about sending the signal for individual DER for reactive power compensation. That's the first thing. So you take in a transfer function form an objective function, and you minimize the objective function with the help of a transfer function which relates voltage and reactive power. So this reactive power, so in this case what we are considering is 3 inverters. large inverters where you can control reactive power. Again, we are putting the active power topic a little bit later. We'll talk about that. So reactive power and voltage can be balanced with the help of this equation. So this is an objective function and this is a constraint. So this objective function is, you can see this objective function, you can represent that in the linearized form. This constraint is, what type of constraint is this? What type of constraint is this? We learned about constraint yesterday. What type of constraint is this? Huh? This equal sign. So what type of constraint is that? Now look at equations, but you, equality, it's equality constraint. See what happens if this is not equal sign? It is non-equal, then it's an inequality constraint. So equality constraint and a objective function. Basically, the equality constraint says that this whole error, which we call it as a Lagrangian error, you wanted to make it equal to 0. So you can take a target node reference. You can look at the voltage on that point, change in the voltage, run through this algorithm, get the controller set point going out for each DER. Okay. How many DERs we are considering? 3 DERs we are considering. What are we controlling? Voltage. Are we sending reactive power from the DER? No. We are changing the reactive power from the, who changes the reactive power? Inverter changes the reactive power from the DER. So we are actually sending inverter set points to the smart inverter basically. How the inverter changes the power inside the inverter, that's the local control or the device level control. We are not talking about that. We are still on that level, not on the. I will tell you probably in the advanced topic on Friday or something how the inverter control really happens, inside the inverter if there is an interest. I don't know whether you have interest there. That's a different thing. So just wanted to keep at that level. So here is a distribution network. We are actually showing DERs in here and 3 DERs. And this is the node of interest. You see, this node voltage is very bad. You want to actually have these 3 DER control this node voltage. So you may ask the question, if this node voltage is there, anybody else can control other than this DER? Well, you see this thing here that can control this voltage. What is this? Voltage regulator sitting there, which is going there. Oh, do you remember voltage regulator? We talked about that. Voltage regulator can control. So that is called a legacy controller. This is DER control. So this is what we are going to do. So we are going to see a change, drop in the voltage, and you wanted to see that the voltage can be controlled back to 1 per unit. So you can see that this voltage is lifted back to 1 per unit because of the reactive power coming from the inverter. So you can actually use this reactive power from the inverter to control the voltage node. Oh, can you use these 3 inverter to control the voltage here? Maybe not possible because that's too far to control. You may need a local, DER to control that voltage. Good. That's one case study of reactive power. Tomorrow we have a session, or maybe even today afternoon, or either tomorrow, I think we have a session where I will show you how this reactive power can be coordinated with this regulator. So if this reactive power is pushed to control the voltage, this regulator also will be seeing that, right? What's the regulator going to do? Regulator is look at the voltage on the load side and control the voltage on the. So regulator is actually looking at this point. So if this 67 is pushing reactive power here, this regulator will be looking at that, right? So which means it affects the regulator operation. So how do you coordinate with them? We'll talk about that. So there is a little bit of challenge there. It's not that easy that you push reactive power and voltage is controlled. There should be some coordination challenge there. That I think we will talk about that. But for now, to answer our fundamental question, can you send a signal to control the reactive power? The answer is yes, we can send the signal. Now, can the signal sending done from the power flow? No, you need a controller. And that's what we are discussing. So where does the power flow comes in here? Power flow comes in here by keeping this reference voltage. It will not do anything how that is managing the reference voltage. You see? So power flow will say, I run the power flow, I say this is the voltage I have currently, right? I need to have this point there. So power flow will be able to tell you what we can do, or optimal power flow will be able to tell you what we can do, how much voltage you need to maintain, and then the controller works. You see the difference? What comes first and why, how it comes. And to whom. So all those things are, I think probably you'll get some clarity now what we need to do. This one is one architecture we developed and implemented. I'm not saying that is the best architecture. It's one method that we are doing it. That's important, but you can do similar methods like that too. Good, makes sense so far. Okay. Now we will do is we will do. I think our friend is not here today. Can you do active power control? That's something which we wanted to talk about. So in the active power control, I am trying to show you something, active power and reactive power for the group of DERs. So now we are doing one DER, right? Than before. You want to see in one group and see whether you can make a load generation balance of that group, fictitious. Okay? It's difficult to do it through mathematics. So you can use at that point some things like machine learning. Okay, so that's why if somebody is interested in using, I don't want to use the word parametric optimization like a genetic algorithm or something. If somebody is interested in using any machine learning methods, you can use the machine learning method to find out the groups. So here we are using a machine learning method to find out if you have a distribution network, how do you make groups? Okay. What is the property of the group? The property of this group is that this group will be self-sufficient with having power in that group. So for example, we have 5 of us. There's a loads connected and we are generators. We want to make sure that within 5 of us, we have enough generation and the load when photovoltaics are connected to take care of the load in our group. So we are self-reliant, self-sufficient. You don't have to depend on another group. We are fictitiously calculating that, meaning we are understanding with the existing resources what will be the power balance, okay, for the PV farm changing. So you have several of us there in the distribution network. PV farms are changing. We are finding how we can make a group such that there is no power exchange between two groups. That's the goal. So if we can achieve that, that means we are self-sufficient, right? So what is this grouping? The grouping is exchange between points and then cut it, then I'm good. Okay. This can be done through, so this is a project that we have implemented in the field. So we tested it in the lab and tested it in the field. And this is an example of the group. So you see these groups making different colors, meaning they are having this different color. These are fictitious, and then we implement it in the field, how it's been done. So you can do that using clustering. Okay. I don't know if you heard this. When we started our day in the morning, 5 o'clock, you have rain. Then we have a heavy rain. Then we started our session a little late. Now we have disturbance here. Door is open. I normally don't talk with doors open, which is a little bit distracting. So if you keep talking and I'm just in the flow and formulating my thought, making sure that you understand, suddenly all this, and then I'm just, we should close it, I guess. Nobody comes now, I guess, yet. We'll have 10 minutes and then probably we are done. Is that good? Yeah. For so one group falling short of power will can happen. So you will be able to use the controllable asset, for example, battery energy storage, to supply that power in the same group. And so you may ask the question, well, do you need a controllable asset in every group? You may not. Suppose you have controllable asset for 5 groups, then that controllable asset in that grouping at all the 5 groups can send signal to each group and then send the power. If you do that, then there is a power flow. There will be some power flowing through that. Correct. Correct. So you can do separate, you can do together, you can do the whole, you can do depending upon whatever level of flexibility you may have for your battery. So let's assume that you have battery in every group, you can do it. So battery in 4 groups together, you can do it. Suppose you have only one battery for the entire district, you can do that too. And what is the trade-off? What's the challenge? The challenge is if you have battery in every group, then your losses are less and controllability is more. Battery size is low. You can actually flexibility is more. So this is one good news. The bad news is that your cost is high because you have batteries in every group. So the tool what is giving you is gives you flexibility on whatever you wanted to do with respect to your asset. Depending upon whatever you have in your utility, you can change. And it also gives you flexibility. What happens if you scale the PV farm? If you have more PV farm comes in future, what will happen? So the groups will tell you whether you need this balance is not, and things like that. So you can do, you can be flexible. You can do either way, depending upon what level of controllability you have. So the utility, when we implemented, utility said that let's start from small, which means let's say that I have only 3 battery and I control only 3 battery. All the PV farms in that feeder, let it do whatever it wants, and I'll control 3. We control 3 for each area. The group that you are making, you do for 5 groups together, and that gives a set point for the 5 group. You divide that into each group and then send the signal for each group. Only thing is that you should make sure that it's tracked, whatever set point it is. And we did that because they want to make it simple for implementation. Make sense so far? So you get to, I'm just doing, so you can actually run the power flow and find out the sensitivity of voltage with respect to the reactive power. You can look at the Q S square minus P square from the inverter, and you can find out whatever the reactive power should send from each inverter for that group. So that's the reactive power, voltage. You can also do the active power. So now I will tell you uh, groups. So this is actually the cluster. Groups are clusters. So you see 1, 2, 3, 4, 5. There are 5 clusters. You see the different colors, right? 5. And then you can see the BESS, which means battery energy storage. We are assuming for each group there is 1 or 2 battery energy storage. Okay? So you have looking at control of the battery energy storage. Now no reactive power available at the DERs to support the voltage. Now what you do is that you started getting reactive power available at cluster number 3 and 9, so 2 locations. Then you see cluster 2 merges with cluster 3 and cluster 5 expands its boundary. Why we do that? Because we have sufficient reactive power. So another case is reactive power available on 3 locations. Then you see forms a new cluster 6 from cluster 5. So you actually have a group, another group. So what it tells, summary is that you can change. So what we do is we run a power flow. Remember that in the utility you run the power flow every 30 minutes. While you run the power flow, depending upon the time, you can also form the cluster. Every 10 minutes, every 20 minutes, we can see what will be the cluster. That is it. So if you have a cluster, you can actually do cluster control. So basically this is optimization algorithm to do the cluster control to give set points to each DER. So this DER set points are, we can actually have batteries. Batteries are working on the set points in this case. We're talking about the battery for every place. You can actually reduce number of batteries. You can look at the state of charge of that DER and you can balance that state of charge. So if you do like that, there is a math algorithm associated with that. You can actually look at the change in the voltage available Q for DERs, and we can also look at the how much Q can supply from the DER. So this is a data. So you get the signal from the field through a TCP channel, and you write a Python routine on a proposed control architecture, running the power flow, developing cluster and sending the set point back to the field. Through the TCP, it goes to the field, and from the field, it actually works on the devices implemented on the field. That's basically the centralized algorithm approach. Here is changing the cluster. You are improving the. So we test this, what we call it net load. Everybody, we know net load, right? What is net load? This means generation minus, that. So in each area, if there is a flat line I see, that means I know that I am not borrowing power from you. I'm self-sufficient. And if there is a spikes I see, which means I am, borrowing. So we call that as a net load. So we want to have a flat line at 0. Oh, what happens if we get a flat line at 100? Which means we are getting power from the utility 100, but it's a flat line. Still it's good because utility don't want to say, oh, my power is changing all the time. It's a constant power coming from the utility. So it's great. So the goal is basically first flat line at 0 or flat line at any other number. So you see that we want to maintain it like that. Now voltage. Voltage, you can actually maintain the voltage with whatever the voltage set point. Ideally, you need a flat line, but if there is a variation, it has to be within the limit. So here is a voltage profile for every node in the distribution network for a period of 2000 seconds. This is the changing with the photovoltaic. This is the voltage with control on the inverters, assuming for the control on the node. And this is the variation in the voltage node with the control and without control. So you can see how much you can maintain the voltage within the limits. The next one is sharing the power. So what we did, then we said that, okay, can we actually share the power with a global objective? So for example, the utility says that I need power through the utility. Have you heard of grid auxiliary services? The auxiliary services? Yes, heard of it. Have you heard of frequency response, frequency regulation? Yes. Frequency regulation is maintain the frequency constant, right? So frequency regulation normally happens get messed up if you have a varying power, right, from the generation or the load for that matter. So to regulate the frequency, utility either conventionally do is load frequency control and the AGC and the governor, the conventional center. When the DER goes in place, the generation varies, not the load. So if the generation varies, you need somebody else to maintain that frequency regulation, which is basically DER. So utility asks, for example, battery or some devices to give extra power to regulate the frequency. So in some places or in many places, battery value is only the frequency regulation, especially in the US, because other people says that battery doesn't have any value because I don't think battery is needed for the PV farm. So frequency regulation, when it happens, it actually can go all the way to distribution network in the form of power. So I can say to the group, I need this power. So not flat 100 kW or 200 kW, I changing power with respect to time. And that you can ask to maintain the frequency. This is called ancillary service supported by devices in the field. So if you have a set point like that, how do you distribute? So here is an example of that, where we can see a set point coming. We call it area reference. Every time it's a 12 o'clock in the afternoon, 15 minutes later, 1 o'clock. So this is a set point. And you are asked to deliver the power from the PV battery combination to honor the set point. So this is the PV output without honoring the set point, that blue. So the goal is now using cluster, you are making care of honoring the set point. And at the same time, error, reducing the error to 0. And now you can see who is contributing to the set point. Cluster 1 is contributing like this. Cluster 2 is not contributing. Maybe at that time photovoltaics on the cluster 2 is not very intermittent. Cluster 3 is, so now if there is no cluster battery, well, it doesn't matter. You can actually use the entire battery together to support for the cluster. If you have a battery on each cluster, you will be able to see how much cluster is self-sufficient or not. Groups. And then this is a feeder head power flow. So feeder head power flow, if area reference is constant, then you don't need to get the power from the substations or beyond that. What else? So that is basically the summary in here, and you can also adjust based on the capacity of the battery running out of juice, which means the battery is low. You can adjust the power based on that battery. So I think we are almost running out of time. I wanted to see if there is anything specific I want to talk about. So you can actually run this for multiple PV farms located at different nodes. So this is assuming that there is a cloud passing and is a distribution network, but this PV farm see the cloud, the other PV farm don't see the cloud. So you will see this intermittency is changing depending upon several PV farms. So you can put that this is the load. So you'll get the net load. Each place is different. So you can actually see what will be the cluster in one time and cluster at another time. So, it's moving with respect to time. And then you can see what will be the power contribution. So you see right here, you see this is the reference. And if you look at here, it's not tracking the reference. You know why? Because there is a high intermittent nature and there is no enough battery capacity. So it's not that you should do everything perfect. You can also see what is the problem, and then you can design solution, meaning you need to increase the capacity of the battery, whether you need to readjust. You could do that. think probably that's, and then this is a voltage profile associated with this. So what we have learned today is two part. One part is we learned how you can extend the power flow to use that power flow to maintain voltage stability or voltage um, balance. Then we started from the power flow. So power flow, optimal power flow, and time series power flow is what we have covered in last few lectures, and using that for stability as an example. Then we started moving that from that to uh, higher level control, we call it tertiary level control or secondary level control. How you can use that set point from the power flow to derive control objectives for an electric distribution system, not the individual inverter as a high level, and then how you can from there give set points to a group of BERs, controllable assets with respect to battery. So that's where we are. Tomorrow when we come back, what we will do is we will use that same framework with the DER, and I will show you how you can coordinate with the other device in the distribution network with control. And then we will go into how you can control individual inverters for voltage frequency balance. And then we will do how to implement it in software. We will try to use a real-time simulator example of how to implement it in software. I think there is a homework assignment which is, I think, due today, so you will be able to deliver that. I will probably give you one more problem to solve using MATLAB or something for tomorrow. So that's basically our plan for tomorrow. In between, if you are in this and thinking about it, and if you want to bring up with any specific area that you want me to attend or talk about, bring that questions to organizers, and we can talk about that tomorrow. So from now onwards, we will be obviously continuing control, advanced topic, real-time implementation. We will also want you to feel it and then ask any questions, anything specific that you wanted to mention. So that's basically what I'm thinking with respect to some. So yeah. Any questions on this so far? Any questions on what we have talked this morning? Very easily. So now, well, it's a very good point. So when we did this, we talked about batteries, right? And several battery combinations. And then we say that the energy storage is used and then power balance happens. The same proposition, you can say that, hey, the battery is not there. You have two pump storage or two, hydro plant. How do you deliver that power? You actually have to model and you got to see the ramp rate of that and then see what will affect and where it can be contributed. That's one thing. You can also implement and see what, suppose you have a inertia dependent source like a flywheel or something connected to it. What will happen to the power swings or power changes and then frequency? So we can plot the frequency on the system also. So yes, it can be extended to other type of energy storage, frequency balancing or load balancing solutions. You can also implement to see what happens. You can also implement on the same model to see what happens if you add a reactive power compensator like a StatCom or some other devices. So the architecture wise, I'm very because this has been vetted by several people. So architecture wise, I think it is it's very flexible. The algorithms or the controllers or the devices, you can use the same model and then build your own framework out of that. But this is kind of a feasible model that we can. Yes. Any other comments? Any other questions? Okay, so we'll disperse now, and we will. I think it's a session in the afternoon, but we'll come back again for the lecture session tomorrow.
Thank you, sir, for your insights on modeling of IBRs in distribution system as well as transmission systems. So thank you to all for